Let's talk about minimum heap trees. This is another application of the binary tree so that information can be stored and retrieved in sorted order very quickly and efficiently. The basic state of a minimum heap tree is that the parent is always less than its children in value. And I'm going to show you how we build a minimum heap tree one step at a time. And each step something is added and then it has to be checked to make sure that we're in minimum heap state. So let's start with 5 as the first element and we'll put it at the top of the tree. Well, it's the only node, so we're clearly in min heap state. Now if we add the 9, it goes into the next available position. And it's always important that we maintain a complete tree. In other words, the last level is all the way to the left. There are no gaps. Well, this is in minimum heap state because the parent is indeed less than its child. So we're good. Now let's add the 3. The 3 is going to go here. So it's obvious that the parent is not less than its new child. So we need to do what's called a heapify process. And this is one in which we make adjustments so that we maintain the minimum heap state. So this process simply means we're going to switch places, and the 3 is now the root node. The 9 remains unchanged, and then the 5 takes the place of the 3. And now we're back in min heap state. So let's add the 4. The 4 is going to go into the next available position, which is here. Clearly, the 9 is not greater than the 4, so we need to heapify again. So we switch the 4 and the 9, and now the 4 takes the place of the 9 takes the place of the 4, and the 5 stays in the same place. Let's add the 6. The 6 goes here, the next available position, and everything is fine because the 4 is still less than its new child. No heapify step is necessary. Now we add the 2, and the 2 goes here. And clearly we can see that not only is the 2 less than its parent, it's also less than its grandparent. So 2 steps need to happen here. The 2 will switch with the 5, and the 5 will go here, and then the 2 will switch with the 3, and the 3 will go here. So the resulting tree is going to be 2 at the top, 3 to the right, and then 5 to the left of it. The rest of the tree stays the same. Now, let's add the 7. Where's the 7 going to go? It's going to go to the right of the 3, and everything is fine because indeed the parent is less than its new child. Now you take a moment and work through adding these 3 new nodes and see what you come up with. I'll wait. All right, let's see how you did. You're going to add the 1 into this position because it's the next available position in the tree to maintain a complete tree. Clearly the 1 is not only less than the 9 and the 4, but also the 2. So it gets to make 3 swaps, and all of these will go down a level. Now, the 8 joins the tree here, and everything is fine because its parent is still less than it. So no problems there. The 5 is going to join here to the left of the 6, and there only needs to be one heapify step to make this happen. So our final tree this is now a minimum heap tree. Now that we know how to build a minimum heap tree so that it is in minimum heap state, let's see how we retrieve these elements very quickly and efficiently so that it is in sorted order. So here we see the tree that we ended up with, and the way that we retrieve these elements is we always take off the root node. We say that's got to be the smallest element in the tree because it's a minimum heap tree. So we're going to take off the 1, and what we're going to do is we're going to take the very last element in the tree and put that element in place of the 1. Now we can see clearly this is not in minimum heap state because the 6 is the root and it is bigger than both of its children. So what we have to decide now is which child should best replace the 6, the 2, or the 3, so that we maintain a minimum heap state. Well, it's always the lesser of the 2 children. So we do this process and say, all right, 2 and 6, you're going to switch places. Now the 6 is going to end up here, and we have to ask the question again, is it in minimum heap state? And the answer is no. Which one of these 2 children should best replace the 6? Well, it's going to be the 4. So the 6 is going to jump down all the way to here, and in this position, it will have minimum heap state. So this is our new tree. Now we are back into minimum heap state. So if we wanted to retrieve the next one, we do the same thing. We take off the 2. It's clearly the smallest element in the tree because it's the root of a minimum heap tree. And then we replace it with the last element of the tree, which is the 8, which results in this new tree. Now, we look again and we see that the root of the tree is clearly not right because it's greater than both of its 2 kids. So which kid would be best to replace it? Well, it would be the 3. So we're going to switch down this way. Now, if the 8 is here, is it good? Is it less than its 2 children? And the answer is no. The 5 is the better one to replace it, so we're going to switch it down to here. So the 8 will end up down to here, the 5 will move up to here, and the 3 moves up to here, with this as our next tree. And now we can see we're back in minimum heap state. Let's do it one more time. Let's remove the top element, which is clearly the smallest one in the heap, the 3. Now, you finish the rest of the process. What's going to happen next? All right, let's see how you did. Well, the 9, being the last element in the tree, is going to replace the 3, and a resulting tree is going to be this. Now, you can see again, this is not a minimum heap tree. We need to restore the min heap state by doing, again, the same thing. Which one of the 2 kids of the 9 is the better one to take its place? Well, it's the smaller of the 2. So the 4 is going to jump up to here, which puts the 9 here. Same thing. The 6 and the 5 are clearly smaller than the 9. Which is better to take its place? The 5. So the 5 jumps to here, the 9 ends up down to here. And so the resulting tree is this. And now you can see we are back in min heap state. Every parent is smaller than its 2 children. And we could continue this process until the tree is totally empty. And I strongly suggest that you do that on your own and see if you can make it happen. So now you know how elements are retrieved from a minimum heap tree, and then the tree is returned to its restored minimum state.